What is a p-n junction diode? A p-n junction diode is formed when a p-type semiconductor when a p-type semiconductor is fused with n-type semiconductor, creating a potential barrier voltage across the is called p-n junction diode. Now a p-n junction diode operate in two different ways, which are the first one is forward bias or forward biasing. Like we have, this is the p-n junction diode, okay. Diode, because we fused or diffused a p-type material. This is p-type and this is n-type. So we diffuse this p-type with n-type, okay, and we have a bias voltage developed here, which is called the barrier potential, which we already discussed in p-type semiconductor. And we have some external electric field, internal electric field also developed, and this is called the depletion layer. And we have the band diagram here, which we already discussed. Now what is mean by a forward biasing? A forward biasing means like if positive terminal of an external battery, this is an external battery, is connected to p side of the semiconductor of the diode, and negative terminal of the battery to n side. Is connected to the negative terminal is connected to the inside of the p-n junction. We have a forward biasing. Now in forward biasing, the forward bias voltage Vf, here we have the forward bias voltage Vf, which I represent by Vf, oppose the potential barrier. It's oppose this potential barrier. Why? We have positive terminal here, so this positive terminal push the holes towards the junction, push these holes towards the junction, and this negative terminal push the hole towards this junction. So as a result, electrons move here, electron move here. So this positive charge density, this region now gone. So we have only this small positive, this depletion region. So due to this, the depletion region width decreases. Now the majority charge carrier holes of P region, the P region is a majority charge carrier, which are holes are repelled by this positive potential of battery towards the junction, and similarly the majority charge carrier of n-type n region, which are electron, are pushed or repelled by this negative potential of the battery towards the junction. As a result, we have the width of the junction which decreases. Now when Vf, if this forward biasing voltage is greater than Vb, this voltage, the biasing, the barrier potential of voltage, then what will happen? Electron will move to the right and hole move to the left, and we have a current which is called forward current, If. The magnitude of this forward current is usually in milliampere. and the resistance of p-n junction is low when we have forward biasing. So this is all about forward biasing. Now what is a forward biasing? When the positive terminal of the battery is connected to the p region and negative terminal of the battery is connected to the n region, then the holes which are majority charge carrier in p region are pushed by this positive terminal of the battery towards the junction, and electron which are majority charge carrier in n region are pushed by this negative terminal of the battery towards the junction. So as a result, the width of the depletion region decreases. But if we increase the forward biasing voltage in such a way that if its value is greater than this barrier voltage or the depletion region voltage, then what will happen? Electron will cross the junction from N to P region, and hole will cross the junction from P to N region, and we have a forward biasing current IF. In this case, the resistance becomes 0. Now what will happen to the band diagram? This is the actual band diagram of p-n junction. In forward biasing case, the band diagram looks like this. Like the initial is this one, which is this. This represent the initial. We have the VB here. But if we apply the forward biasing voltage, then this barrier potential, which is now this one, decreases. Now electron can easily jump from here to here if we apply a small push to this forward biasing voltage. But here the biasing barrier potential is very high, so electron need more energy. Here it needs a smaller energy. Now if this become greater than VB, then they will become almost equal, so electron can easily move from here to there, and this become very easily, so holes can move easily from here to here. So this is all about forward biasing. And next we have reverse bias. And reverse biasing, now this is the normal diode, okay, p-n junction diode. Its band structure is shown here. We have the depletion region and we have the barrier potential of the voltage due to this barrier potential is VB. We have this internal electric field. Now if the positive terminal of the battery is connected to N region and negative terminal of the battery is connected to P region, then what will happen? This is negative terminal, so the holes here will push by this negative terminal away from the junction, and these electrons which are negative and we have here positive, so the electron will push away from the junction. So as a result, the depletion region width increases, and this is VF and this is VB. Now in this case, electron move in this way and hole move in this way, so there is no movement of electron across the junction and no movement of holes across the junction. Now the band structure is here. This is the initial band structure when the junction is in equilibrium. But if we use the reverse biasing, then this depletion region width increases. What it means? It means that this barrier, this potential V, which I call V, which is VB plus VF, okay, is bigger than this one now. Is bigger than this now. So the initial band structure is this, its barrier potential is this. But if we use the forward reverse biasing, sorry, it's a reverse biasing, okay, we call it VR. Use the reverse biasing, then this barrier potential increases, and this increases by this amount VF, which is VR, sorry, which is this one. So the net barrier potential is now VF plus VB, which is much bigger than VB. So it means that now the electron are hardly moved to here, or the holes will hardly move to here, because the barrier potential is very large. And in this case we have a current also, like we have electrons here and we have holes here, the minority charge carrier. We have few holes here and we have few electrons here. So might be this electron will move to this side and might be this hole move to this side. So we have a current which is called reverse biasing current, which can be measured in milliampere. But this current is due to minority charge carrier. While in the case of forward biasing, this current is due to majority charge carrier. So the difference is between reverse bias and forward bias is, like in reverse bias we connect the negative terminal to P side, P region, and positive terminal to N region. While in forward bias the negative terminal is connected to N region and positive to P region. So here's a result. In reverse bias, the width of depletion region increases. Here the width of depletion region is decreasing. Now here there is no current because the barrier potential is higher now. Here the barrier potential is small now. Now the current here is due to minority charge carrier, because might be there are few electrons which will move across the junction and few holes here which will move across the junction. So the current which is reverse biasing current measured in milliampere is because of minority charge carrier, and here the current is due to the flow of majority charge carrier, because the weight of depletion region is decreasing now. So the electron can easily move from here to here, and the hole can easily move from here to here. So the current is due to majority charge carrier, and this is the difference. And this is all about PN junction diode and its kind of biasing, like forward biasing and reverse biasing. Thank you.